I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to the episode number 48 of our Physics Matter monthly online and live series of Physics for Development. So since the COVID time, our webpage have been shining different spotlight over those developing community to promote the global scientific collaboration and to share knowledge on sustainable development and health, fostering as well as those international organizations and providing free access to experts and the public throughout the platform, inspired by this research infrastructure like the Sesame Light Source or global agency like the IAEA, so the International Atomic Energy Agency, or global non-profit organization as well, like the International Union of Pure and Applied Physics, the IUPAP. So my name is Christine Dahl, so I'm working in Sweden at the European Spallation Source. I'm the past chair of the Forum of International Physics at the American Physical Society. And this is this forum which is organizing this series. And I'm also the current chair for this IUPAP working group on accelerator in science and society. So in our panel, today, we have with Alan Hurd, who is also the past chair at the FIP, and he's working, he was used to work also in Los Alamos, but has a bright knowledge in terms of all neutron and beyond information on all those public the presentation that we are going on. So we will have in the question and answer more possibility to come back to our panel. But today, this is the continuity also of our mini-series focusing on the potential of particle accelerator in healthcare, which is indeed how in August, Dr. Sanja Dajanovic, who was explaining us the possibility to beat cancer with the CIST project in the Southeast Europe. And last month, we heard as well Professor Manji Dajan, who was presenting the STELLA project, which was transforming cancer treatment for the low-resource country. So actually, following those colloquia, we had been shaping few proposals and further collaboration around the globe for those healthcare applications. So this is what we will discuss in the second part of this colloquia series. So today, we really have an acronym and more acronym as well. So that's the honor to have with us Professor Igawa, who is coming for presenting us this BNCT. So that's the new acronym. With having possibility from her broad career as well, because she first started as well with a dental license, in Tohoku University. So after that, she had her PhD at the University of Tokyo, and she has been aiming at minimal invasive treatment for the head and the neck region. So she studied clinical maxillofacial surgery and bone regeneration research at the University of Göteborg in Sweden, for 2 years. And after returning to Japan, she was involved in clinical research on boron neutron capture therapy. So the boron part is also the important connection with neutron that we are more used to. But this is applied to the head and the neck cancer. And it contributed as well. So she contributed to the establishment of the world's first BNCT hospital in 2014. As the medical director for this BNCT research center in the Southern Tohoku University Hospital. So in 2017, this neutron therapy research center was established in Oklahoma University, and the research and education for neutron medicine have been promoted then. So in Oklahoma, so the university, it was also designed as the IAEA collaboration center in the field of the BNCT in 2022. And it was hosted, and the IAEA, so this training course on this BNCT in the summer 23. So she has been also contributing to BNCT as the board member of the International Society for Neutron Capture Therapy since 2024. So this is a really impressive profile, and really having some niche and development in this field of the BNCT. So we are eager to listen to your presentation. So, and Professor Igawa, and we could, after those 40 minutes, you have up to 40 minutes, and then we can take the question from the public. And you can also spend time maybe to, prepare your question if you can. Thanks again.
Thank you for the kind introduction. And can I share the slide now?
Perfect.
Okay, great. Okay. Thank you so much again. So, hello everyone. My name is Kazuyo Igawa from Okayama University in Japan. Okay. Today, I would like to talk about the accelerator. Okay. Today, I would like to talk about the accelerator-based system for sustainable quality of life. Okay. So here is today's agenda. First, I would like to talk about the quality of life after cancer therapy. Okay, so look at this. He had a rash on his face. Okay, wait, was it the point option? Okay, sorry. Okay, he had a rash on his face. He thought it might be something bad. So he went to the hospital. Okay. I cannot do it. Okay. Can I do that? All right. Okay. So based on the examinations such as intraoral finding, imaging, and histological examination at the hospital, he was diagnosed with cancer. Then surgical was chosen as a treatment for cancer. Although the cancer was cured, the rehabilitation after the surgery was very difficult. In Japan, 78% of people want to work after cancer treatment, as they did before the treatment. After cancer treatment, 96% of the patients still want to work, and the main reason is to maintain their life. In fact, 53.6% of the patients are working while continue treatment and rehabilitation in an outpatient setting. Therefore, in order to preserve function in cancer treatment, there has been a shift from anatomy-based therapy to the biology-based therapy. The following is an example of transition of management in head and cancer from anatomy-based therapy to biology-based therapy. In Japan, in addition to surgery, immunotherapy and chemical surgery, including BNCT, are now accepted by insurance, increasing treatment options for cancer patients. Then, I'll talk about boron neutron capture therapy for cancer. In 1936, BNCT was proposed as cancer therapy, and in 1951, BNCT for brain tumor using reactor was performed in the United States based on this reaction. BNCT is a treatment that selectively destroys cancer cells using a nuclear reaction between neutrons and boron-10 with little damage to normal cells. The range of energy by boron neutron capture reaction is the size of a single cancer cell. Therefore, BNCT can be said to be a targeted boron-10 therapy for cancer. The boron used in BNCT is boron-10, which is almost non-existent in the human body. There are two types of boron, boron-10 and boron-11, with boron-10 accounting for 20% of the total. Boron-10 is characterized by its much higher probability of reacting with thermal neutron 38-35 than other elements in the human body. That's a neutron cross-section. The boron dose is the advantage of BNCT for tumor tissue, which is result in a high therapeutic efficacy ratio. That is compared to the dose to normal tissue, the tumor can be irradiated with a sufficient dose to be cured in a single treatment. Therefore, early return to society after treatment is possible. Okay, so here is the BNCT procedures. The boron is administered intravenously. The boron is selected, accumulated in the cancer cells. Then neutron irradiated. A reaction occurred in the cancer cell. The cancer cells are selectively destroyed. Okay. So BNCT expected to be able to treat cancer with a single irradiation, unlike other radiation therapies. Thus, accelerator BNCT is attracting worldwide attention as a minimally invasive treatment for cancer. The accelerator BNC system consists of three parts. One, accelerator that outputs protons. Second, beam transportation system that carries the proton to the target. Third, neutron irradiation system that generates neutrons and then slow down to the energy to the epithermal neutron before irradiating the patient. The BNCT system is being developed using a combination of 3 accelerators: a cyclotron, a linear accelerator, and an electrostatic accelerator, and 2 targets of beryllium or lithium. So in Japan, there are 4 accelerator beam systems at 6 hospitals, like this: 1, 2, 3, 4. Each of these facilities will be described in the following section. The Boron 10 used in clinical BNCT in Japan is only BPA, which is supplied by Pharma. And this is just chemical structure. Okay, so first, there is a first world BNCT system using a BPA manufactured by Pharma and a 30 MeV cyclotron with a beryllium target by Sumitomo Industry. In 2020, it was approved for health insurance covered for the treatment of locally advanced or locally recurrent head and neck cancer. The treatment is currently being carried out at 2 facilities: Southern Tohoku BNCT Research Center in north of Japan and the Kansai BNCT Medical Center in west of Japan. From 2012 to 2018, clinical trials were conducted at Kyoto University for brain tumors and head and neck cancers. But treatment is not currently being provided. In addition, same BNCT system will be installed in China next year. This is the BNCT system at Southern Tohoku BNCT Research Center. Okay. It consists of a cyclotron room and 2 treatment rooms. Patients are positioned room, preparation room, and taken to the treatment room. So while irradiation is finished in treatment room 1, irradiation begins in treatment room 2. Proton output from the cyclotron collide with a target to produce neutrons and in the treatment room. Epidermal neutrons are irradiated. Furthermore, epidermal neutrons have been slowed down inside the body. Then thermal neutrons react with boron in cancer cells, and the cancer cells are selectively destroyed. The Kansai BNCT Medical Center also uses the same BNCT system, but it has only 1 treatment room. An extended collimator for treatment has been developed, and the patient can be spent around the 30-minute treatment time in a supine position. The use of the extended collimator shortens the time required for patient positioning for BNCT. The number of BNCT cases increased. So at these 2 facilities, 158 BNCT for locally advanced or locally recurrent head and neck cancer were performed from 2020 to March 2024. Of these, 155 cases were followed up over 2 years. In 93% of cases, the cancer recurred after X-ray irradiation, and in 79% of cases, it recurred after chemoradiotherapy, but the response rate for BNCT was 68.5%, which was a good treatment result. In addition, at the Kansai BNCT Medical Center, BNCT was performed in the superimposition using the eccentric collimator on 15 elderly patients with recurrent laryngeal carcinoma, and 100% treatment effect was achieved. With a single BNCT treatment, patients do not lose their voice, can return to the society early, and are highly satisfied with BNCT. Next is a BNCT system using the BPA by Stella Pharma and a 2.5 MeV linear accelerator with a lithium target by CICS. This BNCT system is characterized by its vertical irradiation, and there is one irradiation room, and the patient position is set in the adjacent CT room. Clinical research is being carried out at two facilities in Tokyo: National Cancer Center and Igawa Hospital. At the National Cancer Center, clinical trials are being conducted with the aim of obtaining approval for the medical device for malignant melanoma and angiosarcoma. Also, clinical trials for FBPA positive recurrent thoracic solid malignant tumor at Edogawa Hospital, a clinical study for recurrent breast cancer has been completed, and a clinical study for FDG positive cancer is currently being conducted. At the National Cancer Center, a clinical trial of BNCT is being conducted for scalp angiosarcoma. Both patients were women over 65 years old of age, and complete response was observed in both cases. Although temporary hair loss was observed as a side effect, it has recovered, and the patient satisfaction is high. This is a case of BNCT using a bolus to treat malignant melanoma on the left index finger of a 72-year-old woman. Complete response was observed. The patient was able to use her left finger without any problem after BNCT, and she was highly satisfied with the treatment. At Edogawa Hospital, the clinical study of BNCT on 5 patients with recurrent breast cancer after radiotherapy was performed. This is a case of BNCT on 61-year-old woman with recurrent breast cancer after surgery, chemotherapy, and radiotherapy, and achieved complete response. No radiation pneumonitis was observed after BNCT treatment. Although further follow-up is necessary, BNCT for thoracic region can be expected. Therefore, National Cancer Center has been conducted clinical trial on BNCT for FBPA, positive recurrent solid thoracic malignant tumor, since last month. In BNCT, it is important that BPA is selectively taken up by cancer cells, and PET scan using FBPA, which is labeled with F18, are effective for diagnosing patient for BNCT, like this. The third is a BNCT system using BPA manufactured by Stella Pharma and an 8 MeV linear accelerator with a beryllium target at Tsukuba University. This is a horizontal irradiation room. In February of this year, a clinical trial of BNCT was started for newly diagnosed glioblastoma with the aim of obtaining approval of the medical device. Finally, there is a BNCT system using a BPA manufactured by Stella Pharma and a 2.64 MeV electrostatic accelerator with a lithium target by Neutron Therapeutic. This system has been installed at Shonan Kamakura, next to Tokyo in Japan, and clinical trials are being prepared for medical device approval. The same BNCT system has also been installed at Helsinki University Hospital in Finland. I have now talked about 6 BNCT hospitals in Japan. Also, accelerator BNCT systems have been developed and clinical trials and studies are being conducted in China and Korea. Let's take a look. Okay. First is a Chinese accelerator-based BNCT system. The BNCT system uses BPA manufactured by Boron and a 2.35 MeV tandem accelerator with lithium target by NewPix. There are 2 horizontal irradiation rooms and 1 vertical irradiation room. In this March, the accelerator BNCT treatment system was approved as a medical device, and the clinical trials for BPA was started from this May. Next is the Korean accelerator BNCT system. Can you hear me? Okay. BNCT system uses BPA manufactured by Interpharma and 10 MeV linear accelerator with a beryllium target by Down Medax. There are 3 horizontal irradiation rooms. From 2022, a clinical study of BNCT is being conducted for high-grade glioma. The treatment results are good. In conclusion, BNCT is a cancer therapy that uses a nuclear reaction between neutrons and boron to selectively destroy cancer cells with little damage to normal cells. BNCT can usually be treated with a single irradiation, therefore early return to society is possible. With the development of the accelerator BNCT system, hospital-based treatment has started in Japan from 2020. BNCT has a high level of patient satisfaction with improvement in post-treatment quality of life observed. Thank you for listening.
And
Can you
thank
hear
you
me?
very much. Yeah, exactly. So thank you very much for this overall presentation on what accelerator can do. So that's very, very interesting. So, and it does indeed complete the reactor part so that we could come back to. So we would like then to open the floor so to question, and then you can write them so in the question and answer section. And otherwise, please go ahead.
Yeah, I'd like to ask a couple of questions. It's very interesting, especially to see the progress specifically with accelerators, because in earlier trials, it has been reactor-based neutrons that have been used, but the accelerator technology, I think, gives much more definition to the energies and the location. So this is good. I'm curious about the one of your early comments that insurance will now accept BNCT therapies in Japan.
Yes.
And so that's a big step. But there are still clinical trials being carried out. So I don't think that would ever happen in the United States, where you have approval by insurance and there are still clinical trials underway. Can you go through a little bit of the challenge of getting insurance to pay for this? What was the key bit of evidence or data that convinced the politicians?
Thank you so much for the great question. Okay. Actually, in Japan, the BNCT insurance is combined with the BNCT system and BPA. So the BNCT system is different. That means the other BNCT system cannot covered by insurance.
Oh, okay. So it's a combination of things.
Yes. So, so that's why the last part I talked about FBPA PET positive tumor and so on. So I think that clinical study will be finished. Okay, for example, like proton therapy or like carbon therapy, we can show the all BNC system is the same neutron energy and so on, and it's gonna be okay for the by health by covered by health insurance somehow. Easy way, I hope.
Yes.
So
Excellent
far,
progress.
yes, yeah. So yeah, we would like to see, yeah.
Indeed, the political aspect could certainly also, or with the IAEA, so maybe being also supported. And I guess that this is important to have showcase. So this is really all the statistics that you looked at and that you showed are essential. So indeed, we were looking at the aspect of the accelerator-based one, maybe because if we think about those small and medium income country, we could think about those also compact accelerator, like some future really good capacity. So now far away from here, from now as well. But then I think this the different reactor aspects are also essential. So how much of the synergy do you have? Because a lot were initiated through research reactor. And how much in Japan, or that you know maybe more globally, are this synergy existing? So can you maybe elaborate a little bit on the reactor part as well?
Okay, okay. So I'll show you somehow. Okay, so a little bit to the other presentation, I'll show you, and then maybe you have some idea, because now there are two reactors. It's still to treat the patient. So I'll show you. Okay. All right. Wait for a second, please.
And then we'll come back to all the questions from the audience. We have a lot, so it's really nice. So thank you. So,
all right.
but we wanted to have this part, I think, as a complement for you as well to think.
Do you want to start from the history or just for nowadays?
I
Okay.
think it might be good. We will add those slides as well in the presentation material. But if you have maybe like some, just like overall view to look at the quantity and the evolution, that might help as well for the audience. Just like in I don't know, maybe 5 minutes.
Okay, 5 minutes. Okay, so I'll little bit skip. Okay.
Perfect. Thank you.
So this is development of reactor-based BNCT, and okay, so now there are lots of reactor-based BNCT before the 2014, so 10 years ago. Okay, so more than 1,400 cases already over at that moment, but now only two China and Taiwan, that's all to treat the patient using a reactor right now. Argentina, maybe not human beings anymore, just for the animals. And then maybe we can skip for the history a little bit. And then so far, sorry for this. Okay, so just the existing treatment I'll show you. So from 2010, reactor-based BNCT in Taiwan was studied. And then after that, they treat a lot of patients so far. So BPA is also using boron as a boron 10. And then reactor was used in the Tsinghua University. So here is the data. So from they are started for the phase 1 trial from 2010 for head and neck cancer, and then also phase 2 trials for head and neck cancer. After that, they started for the recurrent brain tumor and also head and neck cancer for as a salvage cases. Okay, and then they are started for the their reactor was approved by as a medical device in last year. So they are started for the clinical trials right now. So this is the current BNC status in Taiwan. As you know, you can see from there. This is only 9 cases in 2010, but now it's 2020, 2023. The last year, it's almost 100 cases. BNCT patient, 100 patient was treated by BNCT. And you can go for the web pages, and this is a team of BNCT teams, and you can, and then you can pay for it, and then you can contact them. I hope you can hear me still.
Yes, it
And
works.
then okay, and then there are a lot of foreign patients. 34 patients was treated by BNCT so far, and then this is a case, Australian patient, and then first he went to Taiwan for the diagnosis by FBPA PET, and then after that second time he was treated by BNCT at Taiwan. And this is the result of the cases. And you can see the result was very good. And also, they try to for the pediatric cases also. So this is a case for the 8-year-old kids. You see the patient, this is the patient treatment room. You can see the kids just see the drama, and then during seeing the drama, the treatment is finished. And he looks so happy after the treatment. And in that case, also the tumor is shrink very good, and the result is very good. So even though in cell-based cases in Taiwan, they are very good result by BNCT. Also in China, from 2014, reactor-based BNCT in the hospital has been started. And they are also used for the BPA as a Boron 10. And then this reactor, you can use for epithermal neutron and also thermal neutron. So depends on the case. So this is the treatment room. And this is a case at in China. You'll see this is a case for melanoma. So before BNCT, like this, but after BNCT, the tumor, the melanoma is gone. And then the patient is happy for this treatment also. So this is a summary of the latest reactor-based BNCT all over the world. So now there are only 2 reactors for the BNCT. And from 2014, reactor-based BNCT in the hospital in China. And also 2023, the reactor-based BNCT in Taiwan was approved as a medical device. Thank you so much.
Thanks a lot for those additional slides. Very, very useful. So indeed, because in the past, this was maybe all those research, all those development, and then the kind of showcase that you were presenting will, I hope, also give like a potential investment as well with companies in some sense while it is approved. So we have quite a few questions. So I will start maybe from so the question from Reza Mirfeiri, who is asking as well, how can you make the patient sure that he's stationary during the radiation exposure?
Where?
It's in the chat only. So I'm just reading. So
okay.
is the patient so stationary? How much can he move, or what are the technique that you are using so for this boron capturing aspect? But
That is a normal, how to say, that is almost the same, the other radiation therapy, like proton therapy or carbon therapy. So it's almost the same method, actually.
Very good. So then we have a question from Asset Sherman de Vok, who is asking as well your opinion so regarding the perspective of reactor-based BNCT. So this is what you have presented, but what is your own opinion potentially from the reactor-based one, BNCT?
Yeah, but
By
reactor-based,
comparison to the accelerator.
no, but reactor-based BNCT is also very good, but maybe in Japan, we cannot use in the hospital. So, I mean, depends on the country, as you know. So, I think the neutron source, as a neutron source, reactor-based BNCT is very good so far. But the hospital cannot buy reactor in Japan, so no choice to use for accelerator-based BNCTs.
That's a key point, indeed. So how to have a compact and potentially possibility for the hospital to own it. So that's also important to look at this kind of societal and economical aspect for the long term. So thanks a lot for the question. So another question from Hossam Doya was asking, so is there any treatment planning system for the commercial aspect as well for this BNCT? So perspective for hospital, maybe, I don't know, Philips or any others in maybe in Japan. Can you give name?
Yeah, so for example, Ray Station is already medical as a medical device already in Sweden, right? So
Already.
yeah,
Exactly.
already, yes. And now
So
it's yeah.
Very
Also,
good. And we go ahead.
Also, yeah, at Tsukuba University, they are trying to Tsukuba plan and so on. So maybe in the future there are a lot.
Very good. Then from a question from Partha Sharkar, who is asking, so if the BNCT is effective as well for the first stage cancer patient. So how effective, what's the resolution? Because indeed it always a question on how to impact the treatment.
Thank you. Yeah, it's a very good question. So right now, for especially Tsukuba University, the clinical trials for newly diagnosed the brain tumor right now. So maybe the result will coming soon using the accelerator-based BNCT.
Very good. Also from Hossam Donia, so the question about the generator-based BNCT. So generator-based, so is it like reactor? I'm not 100% sure. I guess, huh?
Who is asking that question? I don't see it.
Hossam in the question and answer, Hossam Donia, and he's raising his hand. So wait, what I will do best is to ask him live, and we'll see the power of ICT now, while giving possibility for Hossam to speak, providing that I can find him in the list. Alors, wait. There. Voilà, you raise his hand.
Oh, maybe it's neutron generator. Neutron
think-
generator based. Yeah.
So voilà, so now you have the possibility to speak, Hossam, if you want, because you raise your hand. You can put your microphone on.
Yes, I am now on. Yes, you hear me?
Yes.
Yes, we can.
Yes, thanks a lot. Thanks for your very interesting lecture. Actually, I do. My name is Hussam Dunya, Associate Professor at King Abdulaziz University, Saudi Arabia. I do actually Monte Carlo simulation for boron neutron capture therapy for some accelerator and for generator. Like there are some commercial generator like deuterium generator, and deuterium tritium generator. Some generator we try to put good fluence or good flux for epithermal inside tumor. So we try to simulate beam shape assembly after the generator. After we get the neutron beam, we try to modify the generator to get best epithermal flux for the neutron. So I ask you, what's your opinion about trying to using generator in for this science? If it is possible, or you hear about some hospitals that use this generator like this, uh, how to compare? What's your opinion? And totally, I need your opinion about this field of study.
Sorry,
Do you-
can you hear me?
Yes, I hear. Do
I'm
you
sorry,
get my question? Do you get my
my
question?
phone is some problem. So can you repeat a little bit the question again? Sorry, I cannot.
Yes, yes, yes.
Sorry.
My question about uh, if you feel I use generator in just a simulation. I am a Monte Carlo expert, Monte Carlo simulation expert. I use we can play with generator to get good epithermal flux inside tumor. If you did you hear about generator using in Boron BNCT, and what is the difference? Because generator is low cost. It is very low cost than accelerator and or reactor. The field of generator. What is your opinion about it? Do you hear about it?
Yes. Okay. Thank you so much for the very good question. I think I'm not sure because the some how to say the field of the neutron field. I mean irradiation field. Is that possible to a big field or not?
Oh, okay.
Did you
It
get
is
a point? Because,
yes.
usually very small field, it works, but it's gonna be the human being field. I mean, the big field, the neutron is how to say not good for the BNCT energy and so on. Isn't it?
Yes. Okay.
Can I,
So far. I don't know. Yeah, maybe we need more developed for.
Yes. Someone answer question in the chat. He told that it is not the
Yes,
required fluence is not achievable at present.
no, so far, yes, yeah.
Yes. Yes. Okay. 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 Thanks a lot. Thanks.
Thank you so
Thanks
much.
a lot. So it's excellent to have experts as well in the audience. So thank you so much. So the audience, please
Thanks.
participate and help us to make it really vibrant like that. Very, very
Yes.
nice. Thanks.
Yes. Thanks a
And
lot.
the question indeed for the simulation. So this is also one aspect in terms of all the developing community in Africa, in Nigeria especially, but everywhere in the developing community. Even if the hardware and the infrastructure are not there, you have so much capacity as well for the simulation. So to direct it as well towards the proper testing and theoretical aspect are essential here. So thanks a lot for your question, so Sam. So we'll have some question also from Pablo Villacorsa, who is asking as well about the comment as well on this any kind of new borated compound. So now back to the boron part that can be soon used so in the clinic for the AB, so for the AB BNCT. So what do you think on that? New borated compound.
That is also important. Boron 10 is important for BNCT actually. And then I think in China, they'll start after the BPA, they'll start for the new boron compound. For the new boron compound, they'll start for the clinical study. So we'll see for the result of the clinical study.
So ongoing. Also, there is a new compound.
Yes,
yes. Okay, so we can maybe follow up on that. So also in terms of the BNCT, so a question from Latoya Williams, so asking also if it can be used for any type of cancer. So what are the limits?
Okay, that is a very good question. So, of course, the important in cancer, the boron should accumulate it in the cancer cell. That's type of cancer we need, right? So important is the boron accumulation in the cancer. That's not all the time. I mean,
Good. And then we have a question also in the chat, which is more about a bit like what Alan was mentioning at the beginning. For the boron 10 source, specifically, the steboroin and then the torofalen. So this is clinically approved, or are they only clinical trial?
No, the steboroni, BPA by steboroni was approved in Japan. That
Okay,
was
in Japan.
oh, in Japan. I don't know in other country yet.
And the borofalen?
Mm.
The borofalen as well?
It's the name of the BPA. The borofalen is a name of the BPA by Pharma.
Oh, okay, excellent. Very good. So we have indeed, so the link to the recording will be sent for sure. So we will make sure that we have both presentation also available. Maybe if it's okay also to have your email address. So Professor Igawa, I think it's important to share that. And now we would like also to have the possibility for Laza, so recommend Laza, so for the name, I'm really bad with pronouncing names. So Laza was last month also with us. So as we mentioned, he was one student of the ASP, and he's asking, so the African school, which happened in 2010, where Professor Dojans was also one of the presenter. And we wanted as well to have him to speak up last month. Because he was doing a lot of follow-up as well, so from potentially as well Madagascar being part of the Stella project. So he's asking a question, so which is about the proton treatment as well. So can those accelerators also use for proton treatment, or only for the BNCT?
Okay,
for those
that is a good question because I'm not sure, but so far this is only for the neutron source, I think, yeah, because the energy is different, right? So yeah.
So far. Okay, so we need indeed some people to be able to maybe look at this aspect.
Maybe in future they develop for this is neutron, target things, and this is flash, this is proton. I don't know, but in the future maybe they will develop for that kind of things.
Very good. So I'm trying to look at the question also in the chat in the meantime. So this is about the boron 10 for the P and for the lithium produce as well, the best energy. So for the boron capture, so the deuterium, tritium, so especially not feasible. So that was the answer by indeed Reza Ferzikri for the question that was raised earlier. And the proton therapy, maybe the energy level as well. So you were speaking about on the order of 200 MeV. So this is what can be indeed provided potentially for, this is a difficulty indeed for getting the proton therapy as well to be accessible. So this energy level. But I think now we managed to have compact accelerator that could potentially be also at lower energy and viable. Very nice. So we have, I think, read all the different questions. So maybe I can check if Laza can connect with us this time. I don't know. Maybe that's an opportunity for him
You got it.
to speak up. Because last time, and we see, so maybe before, we have another question from Hosan. So we can pass maybe the microphone to Hossam. So do you have another question? You raised your hand?
No, thanks a lot. I don't have any question, but I'm very interested in her lecture and professor lecture. So I need the email contact if it's possible to get it. Thanks a lot.
Wonderful. Thanks a lot. And now indeed, so Laza, so indeed last time you were called because you had some duty exactly at the time where we wanted to give you the microphone. So it might be the opportunity today to have you with us. And also be aware that so Manji, so the son is also or was in the audience. So potentially she could also join and participate with us. So please, Laza, if you want to say a few words.
Thank you. I don't have a specific question. I think the talk was really nice and very well summarized. But yeah, I can definitely follow up with the Stella collaboration, because even though we are a small group in Madagascar, we are interested in growing in terms of radiation therapy. And yeah, looking at this talk and the potential of BNCT, it's pretty exciting to see. So, but I don't have a specific follow-up question regarding to the talk. Well, thank you.
So thanks a lot, Laza. So indeed, so I checked and Magic had another appointment, so she couldn't stay with us. But as you mentioned, indeed, the possibility for connecting also for Madagascar with the Stella project, so which was presented last time, this new type of BNCT is excellent also. And you were mentioning for the American Association of Physics in medicine, or the medical physics for world benefits. So I think this is two additional associations which are really important for connecting physics with the medical world, and to have them, I mean, speaking the same language, being on the same goal, and having the same maybe plan towards what could be achieved. So indeed, so maybe Professor Igawa, so I don't know how, is it located mainly in Japan, what the different connection with the medical field is, because it might depend of the authority in Japan. So it also some of the limit of the country and cannot be international, but you do have as well a lot of additional organization and association with the medical doctors. As a question, so for you, so Professor Egwaza.
Yes. Okay. So not only Japan actually, because there are international BNCT society we have, and also the international Japan we have a Japanese BNCT society, Taiwan BNCT society, and in Germany BNCT society. There are a lot of things, so we can compare over that. We also PTCO, like particle therapy, the PTCO, there in BNCT society is involved of that things, but also depends on the cancer type, like head and neck cancer, or maybe like brain tumor. There are also those specific organizations, they are related for that also, yes. And also medical physicists, they are also the medical physics congress, they are related for that too, yes. The accelerator and reactor, they are own different society also. So there are a lot of different things. And also boron chemistry, that is the other thing. And they are also related to that thing. So it's a very wide, how to say it, all the things about it.
Can I ask a question about that? What types of cancers are not appropriate for BNCT?
Okay, so far, okay, BPA is LAT1 amino, LAT1, that means amino transport using. So only, how to say, so far, if you use a BPA as a boron 10, the cancer is very good for the amino transporter. That is the boron accumulation for the system so far.
Soft tissue.
LAT1, yeah. If the cancer has no LAT1 transporter, and then that cancer doesn't have accumulated.
Okay.
So far, okay. So maybe the other boron compound are developed, and then they are different story.
Sure.
Very good. And maybe just like indeed one last a connection between accelerator and reactor with as well in Argentina. So as you mentioned, Argentina, Taiwan, and China having as well those different experiments. So with the Commission Nationale of Energy Atomic, so the CNEA. So through the IAEA, I guess, so they are common, I mean, perspective as well. Are you working directly with them, or what could be potential application that could be helpful? So with Argentina.
Yeah, okay, so maybe in Argentina, they also develop for the accelerator BNCT and also reactor-based BNCT, both of them, actually, if I remember, I mean, if I knew. And then in the future, maybe the problem is sometimes reactor facility is very far from the city, right? So it's very difficult to treat the patient, actually. So maybe the animal or like experiment is okay in the far away from the, how to say, town or like, you know, the hospital. So maybe we can approve actually the accelerator-based BNCT in Argentina, and then maybe it's better to install in more near the, I mean, the hospital, or maybe in the hospital or near the town. So that is maybe helpful somehow, I think.
Yeah, exactly. So I think it's a perfect idea, and certainly some of those developments. So again, how to make it so at the connection between the accelerator and the reactor, and maybe all the try as well to be further developed. So with the reactor part. So very good. So there was a hand that was up, some from Maza, but maybe not. So just a few seconds for Maza. Voilà. So you will. You have a hands up, so I will give you the voice. So Maza Malik from South Africa, who will be also our speaker, so in December. So Malik there. There, I allow you to talk. So Maza, you can speak.
Yeah, thank you so much. I do really apologize. I was obliged to, how can I say, attend the two talks in the same time. But anyway, I wish to thank the speaker for her comprehensive talk indeed. My question is the following. Would it be possible to use nanoparticles instead of specific molecules, boron rich? The idea of using nanoparticles is that they diffuse easily within the cell. One, and second is that there is quite a number of centers of boron, and therefore the I do apologize. Well, the point is, there a possibility to use nanoparticles of boron basic materials? Thank you.
Yes, thank you so much for a great question. Actually, one or two groups is also using a nanoparticle, and then they are very good successful insofar as a preclinical study. So maybe in the next stage, they have a chance for the clinical study, I hope.
Prof. Ogawa, we are really interested to embark in cooperation with you, if possible.
Yes, of course, yes, thank you so much.
And what we could do also, Maza, so this would be to use also the light source or the neutron source to be able to develop as well some effective nanoparticles, and that way we could.
Absolutely, you are right. In fact, the idea is to engineer by radiolysis boron-based nanoparticles.
Wonderful possibility, and then to try to see if it's already done elsewhere and to start from there. So we'll so look at that. So I don't see more question in the audience. So Alan, unless you have others.
No, it was a delight today. Thank you very much.
Thank you very much.
Thanks a lot. And I think it's important, indeed, we always look at the physics part mainly, but here we see the medicine, so the human that can be helped thanks to the physics. So that's what I find it even more, I mean, nice to see some really pragmatic way of using physics and particles to accelerate them, to accelerate so the health, the better health of the people. And we have also, by the way, it's an honor to have Yongki Kim also in the audience, so with us. So she's really impressed as well. So by your presentation, she's the APS president currently, and internationally. So she's from Korea, but you see, we try to connect all the different continents, even so thanks for this global warming hub. And we really appreciate so all the work that is ongoing so in Asia, and that gives an idea on where and what we have to bring on the so exactly what is behind you. So thank you very much also, and thanks so Yongki, Professor Kim to attend as well. So I will simply then, so thanks again, so Igawa, Professor Igawa, and I will so share my screen to present the fact that next month, so we'll have with us, so from CERN, so this is going to be live from CERN, Professor or Dr. Luciano Mossa, who is the project manager for that special 70 years anniversary at CERN. So he is a physicist also, so with the Atlas, so spokesperson for the Atlas collaboration, from the ALICE collaboration, and you will hear much more then about all the achievement that CERN has enabled as well over those 70 years. I guess that most of you know this center as well for research in Europe for all the different nuclear development based after the Second World War. There is a lot applied for medical and far beyond. So we will hear a bit more on that on November 21st. So that is, remember, not the last Thursday, because the last Thursday is going to be Thanksgiving, so in November. So 21st of November, we will meet again at the same time and listen to so Dr. Luciano Mossa, hearing more about CERN capacity. So in the meantime, so I think it's time to say thanks again, and to have a possibility to go back to our normal life. So a big thanks, so Professor Igawa, and good luck, and we'll stay in connection. We'll have a lot of those email and answer in the chat, so we'll make it public with Laza as well, so we will follow up. And indeed as well with Professor Dosan and the Stella project, and as well with the IUPAP. So we connect a lot for this international organization. Accelerator reactor together as well for special goals like that. So thanks a lot.
Thank you very much.
Bye, everyone.
Bye-bye.
Bye-bye.